Guys, if you've taken our quality control class, CTC 115, then you've seen this method before. It's method 300.1. This is how we kind of ended that semester. But if you've not taken that class, don't sweat it, because we're not going to be talking about the method as a whole. We're just going to be looking at a piece of the method that relates to the calibration curve. So I'm pulling up method 300.1. This is basically issued by the EPA, and the EPA has basically done what we call a method, and this method can be implemented in any laboratory that would like to test for the inorganic anions in drinking water using ion chromatography. So any lab, whether it's an environmental lab, as long as they've got the approval to do this method at their site, can adapt this method, change it in a way to make their own standard operating procedure that's specific for their company, and then they can go through and report values on what we call these inorganic anions. Now, what I want to do is I want to scroll through. This is a 40-page document, and I want to scroll through the beginning of this document or this method, and we're going to get to a section under definitions called 3.2 Calibration Standard. Well, we're talking about calibration curves, right? So why not talk about calibration standards here? And they've abbreviated this CAL. So in the upcoming 40 pages, anytime I see the CAL letters, then I know that they're talking about a calibration standard. And it says it's a solution prepared from the primary dilution standard solution or a stock standard solution and the surrogate analyte. The cal solutions are used to calibrate the instrument response with respect to analyte concentration. That's basically what we've talked about in this whole series of videos now, right? We've said that we order something from a company, or we start with a stronger solution and then we weaken them down from that point on. They're just throwing out some new definitions here. So a solution prepared from a primary dilution standard. All right, so a primary dilution standard, what would that be? Well, let's say that I'm measuring copper, or in this case, it's anions, right? So let's say that I'm measuring fluoride content in drinking water. My drinking water company is going to put fluoride content in the water to make sure my tooth don't rot out of my head, right? And for a couple of other reasons, but that's mainly one. And this fluoride I'm going to measure. So I'll need fluoride standards. And I need to see how the standards relate to the instrument signal, right? So I'll make a series of different standards, and these are going to be different concentrations. And then I'll run them, and I see what kind of signal I'll get from them. Okay, well, here's the thing. It has to come from somewhere, right? So when I make my series of standards, let's say standard 1, 2, 3, 4, and 5, those all have to come from a specific point. And that point is going to come from a primary standard. And this primary standard typically is ordered, not every time. Sometimes I'll make them, but they are typically ordered. It's easier that way. And they come with what they call a certificate of analysis. This basically means that if I order a 1000 fluoride standard, ppm standard, then there's going to be a certificate that comes along with that that says this is tested, this has been made, we have results that show it is 1000 ppm. So that way you can use that paperwork on your end to say, yes, I have proof this was 1000 ppm fluoride standard, and I have used this standard to make all of my other ones. Right? That is what we call a primary standard. Now, sometimes we'll take the primary and we'll weaken that down to 100, and then maybe we'll use the 100 to make all of these standards. But it has still come from a primary standard that has been ordered most of the time. So we're going to see that in various methods while we work in a laboratory, and that's something that's very common, and that's something that you should become aware of. So a calibration standard is CAL. So once I make the calibration standard and the calibration curve, what else do I need to do? Well, for this method, and like many others, you will often see an initial calibration standard, which is the set that I'm running that makes the cal curve, right? It says it will develop the calibration curves. And then you'll do an initial calibration check standard a continuing calibration check standard, and then a end calibration check standard. Okay, so what are these? Well, let's target these one at a time. Well, the initial means beginning, right? So let's say that I'm in the laboratory and I take this primary standard and I dilute it down and I use this to make my standards with, and I run them, okay? So when I run them, I get a calibration curve, y equals mx plus b. In the method, because it's kind of mandated by the EPA, that's why they release this information to laboratories across the country, right? It's going to say that you should have a initial calibration check. All right, so let's look at that definition in a little more detail. It says that the initial calibration check standard, a individual cal solution analyzed initially prior to any samples, that verifies the established calibration curve. Okay, so what does that mean? Well, the initial calibration check is a standard that I have made. I've not really ordered it. Now, I could order it if it makes my job easier. I can order it and I can run those too, but most of the time they are made. They can be made from a standard and weakened down and diluted down. That's not a problem. But the purpose of the initial calibration check is to say, okay, this is the cal curve that might be saved in the instrument. Yes, folks, instrumentation will create calibration curves for you. We've not walked you down that path yet, but they do. And that instrument can save the calibration curve. And as long as nothing gets majorly tweaked with the instrument, then that calibration curve should be suitable for quite some time, right? And we will know if it's suitable or not by doing an initial calibration check. Meaning that maybe this calibration curve was done 6 months ago by someone on a different date, on a different time. And that cal curve is still saved in my machine. Can I use that cal curve? Maybe. You might not have to prep a series of standards every single time. You could use the cal curve that's in there from 6 months ago, and all your data is still going to be legitimate. But in order to determine that, in order to see if that cal curve is still good, you need an initial calibration check, which means that you make a standard, let's say 50 ppm, and you're going to run that standard on the machine, and the machine is going to tell you the concentration. Or, if you have the data to make the cal curve, all of the standards and all of maybe the absorbances or the signals or the areas that come from the instrument, you have all of this data, and you plot your own cal curve, then you're just going to have to manually do it. You'll take the signal from this initial calibration check and manually put it into the cal curve. It depends on what you're using. And I'll tell you a secret. It's not really a secret, but in a laboratory environment, the instruments will keep and do the cal curves for you. You will not be generating your own Excel spreadsheets as far as cal curves go. You might have some as a backup, but the instrument does a perfectly fine job creating calibration curves and plugging your samples into those calibration curves to give you a concentration. It does quite a bit of the work for you. So this is the purpose of the initial cal check. And if you were part of the 114 course, you've done this method or something similar, and you walk through these steps. And this is the reason why. We wanted to make sure that this calibration curve that you made was legitimate. And if you made a 50 ppm over here and you cross-reference it to a calibration curve that maybe was done weeks ago, days ago, months ago, these should check out. And if they do, that cal curve's ready. That machine's ready to run samples. However, that's not the only thing that you have to do. So if we go back to the method, we also see what we call a continuing calibration check standard. And it says it's an individual cal solution which is analyzed every 10 field samples. And it confirms that that calibration curve is still working. All right? So this method is very specific. So if we follow the method, and we should, every 10 samples that we are running, we should then go in and do a continuing calibration check, which again is something that I have made in the laboratory. So let's say that this continuing cal check is a 50 ppm or 10 ppm. So I'll do the cal curve. Maybe it's already done. My job's finished. I then go and do an initial cal check just to make sure that it's legitimate and giving me a proper number that's close to the value. And it is. Remember to run this as a sample, right? I know it's something that you've made, but if you run this as a standard, it's going to want to put this in the standard curve, and you don't want to confuse the machine, right? So what happens is that you run these as samples. You label them as the cal checks. Now, some software systems, well, they've got multiple menus for you to identify samples and calibration checks and quality control parameters, but I'm keeping it simple. I don't want to bog you down with that detail. All right, so we're going to run this like we do all the other samples. If I make a 50, it should come out to be a 50. After 10 samples, real ones, I'm then going to turn around and do a continuing calibration check. So this is another sample or standard that I have made, but I'm going to run it as a sample. I don't want the instrument to think that this needs to go into the calibration curve, because it does not. I don't want to tamper with the cal curve once it's made. All right, so that means that if this is a 10, it will process the signal, put it into the cal curve and solve, and then it will kick back, oh, you got 9.9. That's good. Maybe that passes. Every 10 samples is what this method says, but that can be determined, that has to be determined by the method that you adapt. It should specifically state this is how many samples you need to do it with. The next one is the end calibration check. And it says it's an individual cal solution which is analyzed after the last field sample analysis, which verifies the previously established calibration curve and confirms the quantification for all the samples analyzed since the last check. All right, well, the same story here. Okay, I'm going to clear this out. And then at the end of this analysis, I'm going to do an end calibration check. And again, this is a solution that I've made. Maybe it's a 25 ppm. I'm going to run it as a sample, unless I have fancy software. And it's going to process this sample. It's going to take the absorbances or the areas, whatever kind of signal. It's going to process them against the cal curve, and it's going to kick me back a concentration. And it might be 24.96 ppm instead. And maybe that's good, and maybe I check off, and then I can wipe the sweat beads off my forehead because everything passes. Now, what's the purpose in all of these? All right, well, if I do a cal curve, the purpose of the initial is just to check to make sure everything is good to go. And then I run samples, right? And the method said that after number 10, you want to do another cal check. And the question mark here is this still good? So if it checks out in the beginning and if it checks out in the middle, then everything in between is probably also good. That's good science. It's good data. All right, well, after this cal check, I continue on, and I continue to run more samples. Well, maybe I have to do another continuing cal check. After number 20, right, 10 in between, I'll need to do another cal check on me. Is that still good? Well, what if it's not? I stop the analysis. If this is not good, then that means I cannot guarantee all of the data in between this check and the last one. I'm going to have to figure out what my problem is. I'm going to have to rerun those samples. I'm going to have to double check to make sure that my data is legitimate. That's the purpose of the checks. something maybe has went wrong. Something has drifted. The machine is not operating the proper way. Something's happening here in this section that I need to address. All right, but if this does check, then that means everything in the middle of here, that checks as well. I can walk away with a good feeling in my stomach. So finally, we would run the remaining samples down here at the bottom. It could be 8, it could be 2, it could be 1, who knows, but keep in mind, every 10th, according to this method, has to be checked with a calibration check. So maybe the last calibration check I've done, and then I only have maybe 2 more samples that are left. After I run those 2 samples, well, I have to do a final end calibration check in order to make sure that that last set checks out as well. So if this does not check out, but the one previous did, then that means everything in this part, in this portion, is not going to check out either. I'm going to have to figure out what the problem is. But if the end calibration checks, then that also means that this last portion of my sample set checks out. And again, I can walk away with a very good feeling in my stomach, knowing that all of these samples are legitimate. All of these samples have been cross-checked with extra standards that I have ran, that I have put into the sample set. And all of this is a requirement with our analytical laboratory work. Okay, so what I'm trying to get across here is that once you do a calibration curve, and we've talked about how to generate one, once you do a calibration curve, then that calibration curve has to constantly be monitored to make sure it's still staying in line. And we do that through these series of these new definitions now maybe for you, called a initial calibration check, a continuing calibration check, and a end calibration check. Each one of these in the quality control department or the quality control area of the method will give you QC data, and they will give you an acceptable window. So that window will typically be in terms of a percentage, and it will say if you make a 50, it should be within plus or minus this percentage of that number. If you make a 10, it should be within plus or minus certain percentage within that number. So all of this is going to be method determined or laboratory determined depending on who you work for. So again, that's what we'll use to go by if it checks off or if it fails. And if it does fail, then that means all of the samples leading up to that point before the last check passed fails as well. So we have to go back, we fix the problem, and rerun them. So that's a little more detail about calibration curves and calibration curve work that goes into an analytical environment. And maybe if you've not taken the quality control course, maybe you didn't know that these existed. And if not, you just learned something. So congratulations. So on the assignment, what you'll find out is that we might have CalCheck answers listed or data, and we'll say, did these pass, yes or no? If they did not pass, what kind of steps would you do to go back and fix the problem and maybe present that data to a laboratory manager? So those are the types of questions that you'll see on the assignment in that particular regard. So good luck with those. It just requires a little bit of math. Does it fit within the window, yes or no? And that's about it. All right.